Good morning, everyone. In previous video lecture, we have discussed Dedekind theorem, which asserts that if G is a group and K is a field, then the set CHGK forms a linearly independent subset of vector space FGK. We have talked about this vector space and this subset. Now, before going to prove one of its application, we just recall the definition of linearly dependent and independent set. Suppose that S is a set containing elements v1, v2, vn, then it is called linearly dependent subset if there exists some scalars a1, a2, an, not all 0, such that linear combination a1 v1 plus a2 v2 plus dot 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 an vn is equal to 0. If a subset S is not linearly dependent, then we call it linearly independent. So we now come to the topic, come to the result which we discuss in this video lecture. If L is a finite field extension of K, then the Galois group of L over K has order at most the degree of L over K. Means order of Galois group of L over K is always less than or equal to degree of L over K. Degree of L over K means dimension of the vector space L over K. So to prove this, first here we use method of contradiction. So first we assume that L is a finite field extension of K. We have observed in previous video lectures and previous content that if L is a finite field extension of K, then its Galois group GL by K is also finite. Suppose that degree of L over K is M, means dimension of this vector space L over K is M. And also suppose that order of Galois group GL by K is N. Then here our aim is to prove that N is less than or equal to M. Suppose that the elements of Galois group GL by K are sigma 1, sigma 2, sigma n. Note that all these are distinct elements of this Galois group. So our aim is to prove that n is less than or equal to m. So we suppose that the result is false. Means n is not less than or equal to m. It means n will be greater than m. So n will be greater than m. One can say m less than n. Now suppose that x1, x2, xm is a basis of vector space Lk over K. Note that this is a basis. It means every element of L can be uniquely expressed as a linear combination of x1, x2, xm. Now we consider the vector space Lm over L, and also suppose that its m elements given by sigma I x1. Suppose that ith element Ci be the element given by sigma I x1, sigma I x2, dot dot dot, sigma I xm. For all I is equal to 1 to n. Note that here n is greater than m. So here we consider C1, C2, Cn n elements of LAM. Now dimension of LM is M and N is greater than M. Remember that if dimension of vector space V over F is N, then any set containing more than N elements will be linearly dependent. So here we use that result. Since LM is M-dimensional vector space and this set contains more than M elements because N greater than M, therefore this set will be linearly dependent. Okay. Now we use the definition of linearly dependent set. Then there exist scalars A1, A2, An, not all 0, such that the linear combination of A1, C1, linear combination of C1, C2, Cn, that is A1, C1 plus A2, C2 plus dot dot An, Cn is equal to 0. Note that 0 element of this vector space is M tuple. So 0, 0, 0. Now we just use equation 1.5.7 here and substitute the value of Ci and using the sum. So observe that in each Ci first place will be sigma I x1. So when we combine them, then at the first place the element will be summation ai sigma I x1. You may just try to put the value of c1, c2, cn and then summing, you have this result. So try to observe this result. Now by equality of M tuples, since this and this both are same, therefore each place will be separately 0. It means A1 sigma 1, just put I is equal to 1 to n, then it will be A1 sigma 1 x1 plus A2 sigma 2 x1 plus dot 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 A2 An sigma n x1. Similarly, at jth place, it will be A1 sigma 1 xj plus A2 sigma 2 xj plus dot dot dot. So here we just write general place. So we have A1 sigma 1 xj plus A2 sigma 2 xj dot dot An sigma n xj is equal to 0. For all j, you may check it by putting the value of j is equal to 1, 2 dot 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 m in this expression, this, then you have this. Okay. So now we use this result. Suppose that x is any element of L. Since x1, x2, xm is a basis of L, therefore every element of L can be uniquely expressed as a linear combination of this, and so x will also be a linear combination of this. Here we use a summation convention. It means b1 x1 plus b2 x2 plus dot 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 bm xm. Note that the coefficient will belong to K because L is a vector space over field K. Okay. Now we just try to compute this by using equation number 1.5.9. Now observe that summation ai sigma ix. We just compute ith element. So it will be summation ai sigma I, putting the value of x here. Then it will be sigma I of this. But sigma i's are k automorphism, so homomorphism, so it preserves addition and multiplication. Also note that sigma i's are k automorphism, means when we apply this on coefficients sigma on coefficient bj, then it will be bj itself. That is sigma I bj is equal to bj for all bj belongs to k. Why? Because this is the definition of k automorphism. Any k automorphism fixes all the elements of k, that is leaves invariant the element of k. So we summation, so we can express this summation this sigma I of bj xj, but sigma I of bj xj can be expressed as sigma I bj into sigma I xj, but sigma I is a k automorphism, so sigma I bj will be bj, that is it will be this. So note that here we apply sigma I on both terms, but sigma I is k automorphism, therefore it can be expressed as this. Now since summation is finite, so we can interchange the summation convention, summation notation. So it may be written as summation bj into summation ai sigma I xj. But sigma I xj, observe that summation, observe that this will be a1 sigma 1 xj plus a2 sigma 2 xj plus dot 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 an sigma n xj. From 1.5.9 we see that this is 0. It means it will be 0. This shows that this combination will be 0 for all x. It means this map, since this map takes every element of vector space to 0, therefore it will be a 0 map. It means summation ai sigma I will be a 0 map. Remember the definition of 0 map. Now observe that every sigma I can be viewed as character of L star in L. And also we have observed that by Dedekind theorem that set of all characters, distinct characters, forms a linearly independent set. So since sigma 1, sigma 2, sigma n are linearly independent, so this combination, this equation shows that each coefficient will be 0. Why? Because this follows from definition of linearly independent. If any combination is 0, then all the coefficients will be 0. So by the definition of linearly independent set, we have all the coefficients ai will be 0. But you know that from here, you know that AIs are not all of AIs are not 0. So here we found that all AIs are 0. It means we get a contradiction. It means our assumption is wrong. So the result is true. Thank you. I hope that you will understand this result. Okay, thank you. We will meet in next video lecture to discuss this result. These results are fundamental results of Galois theory and are most important part of Galois theory. So we will discuss this theorem in next video lecture. Thank you. Namaskar.